Good day everyone. My name is Jamel Nawaz from BS Computer Engineering, second year. This is my chosen topic, which is parallel resonance. Introduction. What is parallel resonance? Parallel resonance is a resonance condition that usually occurs in parallel resonant circuits, where the voltage becomes a maximum for a given current. Being a parallel resonance means the impedance is high and inrush surge current relatively low compared to a simple capacitor. That picture is based on parallel resonance example, which is inductive, capacitive, dynamic impedance, frequency, and circulating currents. Resonance, considering only the harmonic current spectra given in table 40.2, it would appear that a large number of harmonic-related power quality problems are on the verge of appearing. In reality, most current drawn by many residential, commercial, and industrial customers is of the fundamental frequency. The amplitudes of the individual harmonic currents in percent of the total fundamental current are often much less than the shown in table 40.2. For this reason, end-use locations employing nonlinear loads often do not lead directly to significant voltage distortion problems. A parallel resonance in the power supply system, however, changes the picture entirely. Series and parallel resonance exist in any AC power supply network that contains inductances and capacitances. The following simple but usable definitions apply. Number 1, series resonance, which occurs when the impedance to current flow at a certain frequency or frequencies is low. Number 2, parallel resonance occurs when the impedance to current flow at a certain frequency is high. Digital analog circuit design. Multiple capacitors. The practice of applying decoupling capacitors of different values in parallel is controversial. Historically, you would use a high volume component for low frequencies and a low value for higher frequencies. Unfortunately, this creates a situation where the inductance of the larger component causes a parallel resonance and hence a high impedance, with the capacitance of smaller components, so in the mid-frequencies there is an unwanted peak in the decoupling impedance. One approach with modern MLCCs is to use a substantial number of fairly high-value components of the same value across the board in the smallest package available. On the other hand, a high equivalent series resistance at resonance is desirable to damp the related impedance peaks. Having many capacitors with the same self-resonance reduces the overall ESR and leads to higher impedance at the peaks. Choosing multiple values maintains a higher ESR over a wider frequency range, improving the damping. 2.8 resonance. It is a condition in the power system. In this condition, system is inductive, reactance is equally to capacitive reactance at some harmonic frequency created by nonlinear loads. During this condition, cyclic energy transfer between the inductive and capacitive elements in the power system. This phenomenon is called resonance, and the frequency at which the resonance phenomenon occurs is called resonance frequency. The condition for resonance that occurs in the system. Problem number 1. This is my sample with answer. Number 1. For the parallel resonance circuits shown below the value of resonance frequency. This shown on the picture, the VA is equals to 10 volts. The C is equals 162.11 PF. Letter L, 100 UH, and R is 7.85 ohmmeter. So what is the answer? Letter A, 1.25 mHz. Problem number 2. For the parallel resonant circuit given below, the value of the inductive and capacitive reactance is blank. It is shown that the picture VA is equals to 10 volts, letter C, 162.11 pF, letter L, 100 UH, and R is equals to 7.85 ohm, and the correct answer is letter C, 785.394 ohm XC, 785.417 ohmmeter. End of my report. Thank you for listening. God bless us all.